But there was plenty of room on the bottom to add the lines that were missing. Thank you so much for doing this. Well, we'll see how it goes. Thank you all. Let's go. All right.
Hi, everybody. Thank you all for being here. We're so glad that you could come. We'll continue on our day with Visions 2019 with Sile O'Modhrain, Associate Professor at the University of Michigan. Thanks, Sheila.
Thank you very much. Is this okay? Can everybody hear me? Okay. So what I would like to talk about today is the work around some work we're doing, I suppose I would call it. The last number of years I've been involved with a team at the University of Michigan, some of whom are here. Alex Russamanno is here, for instance, in developing and trying to develop a full-page tactile display. And we're certainly not the only people who are trying to do this. So I think all of us in the area, everybody trying to do this, realizes that one of the things that's going to be a challenge for us is trying to think about what it's going to be like to both develop content for these displays and also to actually design interactions for them. And so that's what I want to focus on in this talk. And I want to talk about the things that we've sort of learned along the way and some of the questions we know we haven't answered yet. And there's probably lots we haven't even managed to even formulate yet. So this is really a kind of a white paper, I suppose you'd call it, on where we're going with these kinds of devices. Let me see, yeah. Go on. There we go. Let's see. First, it's not talking to me. Oh, it's in protective view. Alex, could you give me a hand to get this out of protected view? Because the screen reader can't read it when it's in protective view, which is kind of annoying. Is it protected? Isn't it?
I can't tell one way or the other, but because it's not reading, obviously.
It's not reading that.
Also, I can tell you where you're at.
But yeah,
slide. This is how much displays.
Yeah, that's okay. Great, that's fine. Okay, so the first question that we need to answer when we talk about building a full-page tactile array is, do we need it? Do we really need it? It's going to be a lot of effort, it's a lot of cost, and we want to make sure that at the end of the day, for both the people who develop these displays and the people who are ultimately going to have them bought for them or buy them themselves, it is an extremely, at the moment, it's likely to be a significant increase in cost, although one of the things we're trying to work towards is making sure that that doesn't happen. But at the moment, that's likely to be the case, at least for the early devices. And even when we think of a single-line device, we know how expensive these are, although we're starting to find ones that are cheaper now. But myself and Alex and other people who go around conferences, you know, naively, a lot of people would come up and say to you, well, why do you need a full line? Because when you're reading Braille, you've only got two fingers in contact with the surface, so why not just have two cells? And any Braille reader is just going to go, what are you talking about? But, you know, we always have to explain that it's not just about feeling the character under the finger, that there's so much more to reading than actually just the character that's in focus. And so in order to try and basically do a myth-buster job on this, we came up with a very clever set of apparatuses, I suppose you call them, to test this. And we wanted to look at two things in particular. One, we had the idea that one thing that was important about reading Braille was being able to move your hand over the surface of the page and feeling the changing dots as your finger moved. And the second thing was possibly there's information in the way that your hands and arms move that give you the ability to locate things on a page, for instance. And so we took these two things apart and looked at them separately. And the way we did this was to first create a single cell device that just literally you put your finger on it and the Braille changed underneath it. And for many of you who've used a sort of the Braille cell model of a watch, you'll be familiar with this. You don't move your finger very much at all. The Braille kind of refreshes underneath it. And while it's readable, it's not that readable. And so that was one model. And the second, so that was testing the idea of, do we need movement between the page and the finger? In that case, we took away the movement. But we can also take away the movement between the finger and the page, but leave the movement of the arm. And we did that by putting that single cell on a little cart. So you can move your arm along the line, and the Braille would change, but it wouldn't be because your finger was moving. It would be just because the thing was in a different position and a different letter popped up. And so that was another thing we did. Both of those then had no motion between the finger and the surface. And then we compared those with two cases where there was movement between the finger and the surface. One where your finger stayed still and the Braille went underneath it. So that's no arm movement, but changing Braille. And then the other, which is normal, where your arms move and you get Braille changing. This sounds a bit complicated, but ultimately what we found out was that the most important thing in Braille reading is having the ability to move your fingers over the Braille. And both of the, even when your hand was still and the Braille moved underneath it, that was still more successful than either of the conditions where your finger didn't move. So we know that we can now sort of point to people and say, no, it's not good enough to have a single cell. You have to have at least movement, and the easiest and cheapest way to get movement is to have a full line of Braille. But it also provides you with context, because even though you're only reading what's under the finger, you're sort of anticipating with your other fingers what's coming next. So for all those reasons, we know at least we need to go from a single cell to a single line. The question then is, why would we bother going from a single line to a full page? And this next slide, there we go.
Go one more, Sheila.
And then make it go.
Yep.
So, is it running?
Yep.
So, in the 1940s, somebody called Eatman did this study where she looked from underneath a glass table at somebody reading Braille. And for those of you not able to see this, it's basically me reading some Braille. We basically ran her experiment. And you can see my fingers moving across the text as I read. And basically what I'm trying to demonstrate here is what Eatman showed, which is that for very fast Braille readers, you use what she called a butterfly technique. So, you know, those of you who are readers will understand this. As you get to the end of a line, your other hand goes back and starts to read the beginning of the next line, and then they read the middle of the line together and they separate. And so you keep getting this thing. If you're looking at somebody's hands, they appear to separate, come together, as you go down the page. And this is very efficient. And so a full page tactile array would certainly allow that technique to be used again, and that would be one reason for doing it. But it might not be sufficient to justify the extra investment. So what we're really interested in looking at is the ability to render tactile graphics and dynamic information, something that you can't do with static charts and graphs and maps. So that's the area that we think these displays are going to have the most effect, is in rendering the spatiality of information, not just the sort of content. And so that's what we've been focusing on as we've been moving forward to do that. I'll make this stop and go to the next slide. Okay, so we have now the beginnings of a reason to do this. And the next questions, the next question we asked then was, okay, if we're going to have a full page Braille display, how many dots do we need? What is the density, the dot density that we're going to require if we've said that one of the things we want to be able to do is to have tactile graphics as well as Braille? And this is a challenge because for most of the existing ways of building Braille displays, it's hard to make dots that are close together. Because in order to do so, the means of moving the dot has to fit under the dot, and that's a technical challenge. One of the things we're doing with our system is trying to find a way around that doesn't involve any mechanical parts, because that's usually the stopping point, because they're the things that are hard to fit into a small space. So if we can avoid the need to have mechanical parts stuffed into an array, then we might have some chance of getting a higher density. But even still, there are sort of reasons to do with how we perceive tactile graphics that would help us discover how dense this array needs to be. And much of this work at the moment is coming from the area of printers, of printers for tactile graphics. John Gardner, for instance, who runs the company that make the View Plus, has determined through a number of studies that you need at least 100 dots per inch to be able to render faithfully lines that can curve in any direction. And so that means you don't get the sort of breaking up of a curve that you do, you know, when you try to do a curve on a Perkins or some other kind of array-based display. So anything with the dot density of Braille is not going to allow you to do smooth curves or smooth diagonal lines. So we know we need finer grade than that. So 100 dots per inch seems to be, at least for Braille printers, where they're going. And I suppose it would be a good enough benchmark for us too. The second thing that John Gardner suggests might be useful is being able to have dots of different heights, because that allows you to be able to create texture and shading within your images that gives you an extra, you know, multiple levels of being able to convey information. So you have spatiality, and then you've also got this textural element, which opens up new possibilities. So that's something else that would be nice to be able to build in. But if we have a very dense dot array, then one of the big problems is, of course, how do we make Braille? Because if we've said we're going to construct our display so it's good for graphics, the downside is that very small dots aren't good for making normal size Braille. So one of the things we tried, again in our Mythbuster approach to life, was to say, okay, if we have to make Braille out of lots and lots of tiny dots, what are our options? And a number of years ago we ran a study where we built up Braille characters in a number of different ways from tiny dots. And we had people read a bunch of sentences to determine if any of these approaches would work. Now, we're not here talking about reading a novel with this new font that we've created, but really just giving us the flexibility to both construct tactile diagrams and also label them. Oops, sorry. And so the things we tried, well, we tried keeping the outline of the Braille cell and just creating a sort of a solid version that kept the shape of Braille but didn't have the internal dot structure. We tried having internal dot structures that were made out of little dots. So each dot was a sort of conglomerate of a number of little dots, but they could be either X's or diamonds or squares or lots of different things we tried. We obviously had standard Braille as our sort of, you know, starting point. And then the last thing we tried was to say, let's keep the spacing of standard Braille, but let's make the dots just out of whatever, you know, the individual elements we have. So they turn out to be very, very pointy. They would be they would be correctly spaced for Braille, so the relationship between each dot would be fine, but the dot itself would be very, very pokey, as we called it. And we tested all these things, and what would you expect might the answer be? Anybody got any thoughts? No? Well,
Not real successful.
it wasn't too bad. It was surprising. We were surprised. What people liked was, actually, they didn't like any of our blob conditions or any of the things we made out of lots of dots. They found it kind of confusing. It was just blurry. Yeah, but pointy Braille was okay. If we had to compromise, the sort of conclusion was that if you had to do it, the best way to do it would be to preserve dot spacing and dot height, but to compromise on the diameter of individual dots. And so that's probably one thing that we think we might be able to do.
So I want to ask, so you're saying the pointed dots, you'll be able to fill the dots much better than the way you have them now, kind of smooth?
Well, they're pointier than the dots you have now, but basically because in this high density, in this world with lots and lots of dots to allow you to make graphics, the dots themselves are tiny, so they don't feel good for Braille if we just made tiny, tiny Braille. The question is, could we make normal size Braille but with small dots? And people seem to think that that was okay.
And you can fill it, and you'll be able to fill that better?
Well, it won't be any worse, let's put it that way. It'll be a bit spiky and you wouldn't want to read a novel.
Well, the reason I'm asking is because I want to learn Braille.
Huh.
Learn some Braille, which if I can get somebody to help me too. But the tiny dots, sometimes very hard to feel.
Yeah.
I'm a diabetic, that's
Yes.
what I was asked of you.
I wonder, that's an interesting question, I think.
So that's where I'm having problems
Yeah,
of learning it. I can remember where the dots are, but when it comes to reading it,
Yeah.
I have problems filling those dots.
that is an
And you
interesting
mentioned
question.
the pointed, that's
Pointy
why I was
Braille, would that
asking
work?
that.
I actually, I
Yeah.
don't know, but it would be certainly worth trying, yeah. So, what was I? So we talked about the idea of being able to create high density graphics and then label high density graphics. And am I at the bottom of that slide? Oh, I wish it would read it to me. It won't. Can I go on, Alex?
Yeah. Now this is the EPH device.
Yeah.
interacting with content.
Yes. So the question then is, okay, so now that we have the content, the advantage of these full-page tactile arrays is like single-line displays, that you can make these things change. So unlike a diagram that you might get prefabricated, you can't make any change to that diagram, and you certainly can't label it yourself. But the advantage with these full-page tactile arrays is that you have the ability to generate your own tactile diagrams as well as getting them pre-delivered, and also then of being able to relabel them and resize them and do all of these things. And so when you start to be able to interact with this content, this also raises a number of questions. And one of them is very interesting for any of us who work in the area of designing computer interfaces. It's quite an eye-opener, literally, because it's the question of what is the difference between context and focus when you think about vision versus touch. So when somebody looks at a display like this PowerPoint display here, there's a sort of a sense in which you get an overview of the shape of the slide and whether it has any pictures on it or whatever, and then you focus in on the content and you might start reading the text. But if I put my hand down on this page that I'm reading from, my hand has focus, and in order to figure out what else is here, I have to search for context. So it's the opposite way to the way vision works. And that might be important as we start to design the kinds of things you might want to put on these displays. We might want to be more aware of the fact that when you put your hand down, you've got focus, and then you have to search for context. So we might have to build our interactions around that. And it's kind of significant because, as I'll sort of point out later, that this moment for us, as we move towards full-page tactile arrays, is about as significant as the movement from a command line to a graphical user interface was for sighted people. It also required us to completely think about rethink how to interact with computers. And so at this moment, we're having to do exactly the same thing. We're having to build all this knowledge up from virtually nothing. And so context and focus is certainly one of the things, and as I'll talk about later, this has implications for all sorts of aspects of managing information on these displays. But it also might have information or implications for how we even design the things in the first place. At the moment, typically when these displays refresh, they'll start, they're quite slow still, so they'll start refreshing from the top up downwards, and they'll start at the top left corner or the top line, and they'll sort of trickle down. And you kind of have to wait till they're done, and it could take a couple of seconds, which is kind of slow. And you could possibly, one thought is that you could possibly increase the efficiency of these displays. You might not be able to change the refresh rate, but if you knew where somebody's hand was and started refreshing from that point outwards, maybe the person would actually be able to start interacting with the display and getting meaningful information before the whole thing had completely refreshed. Or, for example, you could have an outline come up first so you could orient yourself, and then as you did so, features would sort of fill in so that you could have enough information to stay oriented, but maybe the detail would just come along half a second later or something. But it's all about thinking about how to compromise, how do you trade off the fact that even still these things are going to be a bit slow, but we could do a better job of making them more efficient, even in their slowness. The second thing is, the cursor. So now when you use a single line display, if anybody has, you're familiar with cursor routing. And again, this goes back to the question of context and focus. If you're looking at a screen and you're trying to find the cursor, you'll get sort of the context of what's on the screen and the cursor will be highlighted and you'll see it. But if you have your finger on a display, that's a very inefficient way of finding the cursor. So cursor routing is the sort of, it sort of implements this upside down context and focus thing by allowing you to bring the cursor to you. Instead of having to search for it, which is what takes time, you can make it come to you. And that's still, we think, going to be useful in these full page devices, because whatever about searching a single line, searching a whole page is going to even be worse. So cursor routing is going to be really important. But also, even if you want to leave the cursor in place, for some things you might want to do that, we're looking at things like having blinking cursors, so the cursor pops up and down where it is, or having, if we have height available, as we do on the APH device that we're working with at the moment, that you can actually search just for a higher set of pixels, which will tell you where the cursor is. So that's sort of one method of getting around this. Then there are more classic things like pan and zoom. As anybody who's used a map on a mobile device will tell you, that the smaller the amount of real estate you have available, the harder it is to manage pan and zoom. And it's because, going back to the question of context and focus, when you're trying to move an image, you're separating the context from the focus in time, because you're moving either the image or the image across the display, or a sort of a virtual window across the image. But either way, you're losing your bearings for some, in some sense. Visually, there are all sorts of methods for orienting the user as the image is changing, and we don't yet have the equivalent orientation mechanisms figured out for the tactile domain. So that's certainly something we need to work on, and we need to figure out, you know, what is meaningful if you want to be able to sort of scoot around an image and zoom in and out of it. How do you stay oriented? There are a couple of things we already know from the work of people like Nick Giudice, such as if you're zooming, one thing that works is to always keep the image centered on the center of the display, so that it will zoom from the center outwards, and you can always stay oriented. So that's sort of one thing we can carry over from what we've learned. Next, zooming and panning. Something like that. Sorry, Braille is inefficient. Information density. So here's another thing that's a problem. I can probably move on here. As you'll know, anybody who knows, and somebody even mentioned this earlier, when you have a tactile diagram, it's really hard to fit labels on. And also, because Braille takes up, it's a font of static size. So even though you can zoom the image in and out, the Braille font's going to stay the same size. And that's problematic. So one of the ways we've been sort of experimenting with this is to say, well, why don't we just keep the spatial content in the tactile domain? So we'll make a spatial rendering of whatever it is you're working with. And then when you touch it in different places, you can hear, it'll tell you what is the label of the part of the diagram, or in our case we did a crossword, so what is the clue of the crossword, or what is contained in your Excel cell, or something like that. So you have a marker to say there is some text here. If you care to listen to it, you can either single or double tap or whatever. And this illustration here is the periodic table. There's a nice version of this which just has a blob for every element, and with its, I think it has its element abbreviation, and then it uses the Microsoft Scribe, and when you tap on it, it'll tell you the name of the element, and if you double tap, it'll give you more information. If you triple tap, and that becomes a really information-rich spatial rendering, where you keep the relationship between the elements as it would be in the original table, but yet you load it up with all the information that a sighted person could get from the way that the tables can be organized visually. So that looks like a very promising way to go. The nice thing about that too is that naively people would assume that spatial information is really only useful for vision, but as any of us who work with tactile diagrams know, that's not true. It's just that the way spatial information has to be presented is different for vision and touch. And so thinking of ways to, even beyond Braille, you can imagine the case where you could have a screen reader, for instance, in an Excel file, but have the tactile version of the Excel file right there by your hand, so that you could have both the capacity to move around the Excel file using all your screen reader commands, but also then do things like compare columns, select things, apply a formula, using gestures on the actual surface. So you can basically share the information between touch and vision. And we think that that might be a very efficient way to use these displays as well. Yeah, that was that point. Do this. Too many pages. Right, okay. Static versus dynamic content. So with these new displays, I'll just move on. No, that's good. With these new displays, we have some a capability that we didn't have with maps and charts, which is that things can change. In other words, you can have a diagram that might have a simulation as part of it, or even something that's updating dynamically. But that's challenging for touch. Again, think of this context and focus idea. If you have something like a swinging pendulum, then the problem is as you're exploring it, it's changing. So you're moving to figure out how it's changed, and so the question is, can you actually observe both the form and the motion of the object simultaneously? It's kind of a classic problem, really. And so there may be ways that we have to present information such that both of those things are always available at the same time. These are certainly open questions, and we'll have to grapple with these if we're going to make these displays really meaningful. And of course, the other side of it is something that we're much more familiar with. Let me move on to the next slide. There we go. There. Okay. Yeah, so here we have, this is an example basically. So the difference between preparing a diagram or a map or a chart to be viewed versus to be felt is something that transcribers are very familiar with. And for those of you who can see, what we've done here is we've two images of the tube map, one of the London Underground map, one of which is the classic one that everybody uses, which is a sort of, tubes of paint kind of thing. And then the other is a picture of the tactile map. And you can see these are very different. The tactile map is compromised quite a lot in terms of detail, and even in terms of the shapes of the different lines that it renders. But it's meaningful because it preserves enough relational information that you can actually plan routes and figure out where lines cross and use that spatial representation functionally for what it's intended. And so as we move forward into this domain of dynamic tactile content creation, there will be things for which these tactile displays are good, but there will be things that they don't work for either. And it's going to be, I think, really important for transcribers and users and everybody to keep talking to each other, and for the transcribers to keep pushing on us to say, no, we need more functionality here because we can't do X, or this isn't allowing us to do Y. And all of us are kind of moving into this new land of changing content and figuring out how to manage these various new challenges that are going to come up to meet us. Yeah, and one of those challenges is that all of these current displays, as I mentioned earlier, are sort of grid-based, and at least for the foreseeable future, this grid is likely to dominate the way we think. If we can get it really fine, of course, we can move away from the problems we will have when we want to draw nice curves and sideways lines that don't lie on the grid. But we might have to come up with some ways around that. And then, of course, there's a whole side of producing content, which we might be able to rely on automation to do a certain amount of this for us up front, to actually take a visual image or even a partially processed image and render it properly for the capabilities of a given display. So that, in the same way as screen readers use different Braille displays and organize information for, 20 cells versus 40 cells or whatever, there might be equivalent advantages to having some software layer that can do some of that processing for us. But it's only going to work if transcribers and users are involved in its design, because otherwise it might, use artificial intelligence to do wonderful things, none of which are actually practically useful. So that's really sort of, I think that's, as well as the hardware, that's a huge part of where we need to go. So to summarize then, The sort of advent of these full-page tactile displays is, as I said, is significant for us. The transition to these is as significant for us as the transition from the command line to the graphical user interface was for people, using who can see screens. And as with the graphical user interface, this transition requires us to come up with a whole new set of methods for managing the content and the access to content that these displays can provide for us. And the bottom line is that it's actually a really exciting time to be involved in Braille and tactile graphics, because it's been a long time since we've been faced with the possibility of innovating to such a huge extent. And just before I go, I want to acknowledge the team at Michigan. Alex is here, Brent, a whole bunch of people, Frank Gillespie, Val Morris, our former colleague who passed away, Rishikesh Rao, and then also to acknowledge a number of funding sources from the National Science Foundation, the University of Michigan, and Help in Kind from the Smith Kettle Eye Research Institute in San Francisco. So that's all I had to say, and if anybody has any questions, please ask.
I just wondered how many lines of text you need to do the butterfly reading technique.
Well, I think you can 3 or more would be, even 2 you can kind of do it, but I'd say 3 or more lines, it starts to become efficient.
Is that what you use to determine what would be a full screen display?
No, a full page display we consider to be something that can render close to a full page of Braille, which is, in this case, it's what, 32 characters by 26 lines or something, or something of that ilk. So a full page of a Braille book as opposed to a print book, because that you need that amount of space. If you're going to do anything with graphics, you need that amount of space. Basically.
Have they perfected the piece of equipment that they've been working on for a while? Because a lot of us never heard anything after they started producing it. They had phototype and that kind of thing, but then
they being
Michigan.
Oh, Michigan, yeah, we are the company that's doing it, and it's
off the face of the earth for anybody that didn't know who to, what it was called, who to talk to.
Yeah, well, Alex, do you want to?
Wonderful thing.
Sure, yeah, just quickly. So Sheila is the co-founder of the company, and myself included, as well as Brent Gillespie up here, and it has been sort of dormant. We received funding recently and are working to develop the technology that will eventually lead to a full-page display. So it is alive and well. If you have questions, I'm happy to answer after. Again, my name's Alex, and I can meet you after we talk.
And they were using, they said that they were using a technology where the dots would, like something would cause the dots, like air would cause dots to raise.
Yeah,
that's it.
That is correct. And,
yeah, well, I heard about it a few years ago, and I wondered what happened, because they kept talking about this wonderful orbit display and all these things, and I was like, where'd they go? And
well, it's we had to sort of, we got the bubble bit working, and then we had to sort of hide for a while we got the way of controlling the bubbles working, and then we had to put the two together. So
I think it's really awesome.
we hope so. It's still, we don't underestimate the challenges that are still in front of us, but we're going to give it a shot.
Do you have a prototype?
We don't have a prototype with us. What I do have, though, and I wanted to let you know, is I have the APH device that we have been working with, which is the graffiti. So if anybody hasn't seen it, we found a little spot on table 20, and I'd be happy to show, just so you can get a sense of what these things are like. The other shameless plug I'd like to make is that we're always, as we develop these things, we're always looking for people to help us try them. And if anybody can reach us in Ann Arbor and would be willing to give us contact details, we'll add you to our list of people to contact when we need work. We've also got another drawing project going, which is kind of cool. It's a project to allow students in schools to label and draw their own graphics. It's not quite the same technique, but it's
That's the haptic.
I have a question. You talked about being able to produce curves and stuff for graphs and different things like that, and diagrams, what have you. And of course, that's a real important part. Do do you anticipate having one Braille display serve all these purposes? Or would you produce one display that's mainly for, reading purposes and another one that can do both, or haven't you decided?
We have a couple of ideas. It turns out that the way we're doing this, it's possible that we could actually have different layers that you could put on the top, one for graphics and one for Braille. So that's one way of thinking about it, that the base display is kind of the same, but you overlay, whether you're primarily doing graphics and you have to deal with pokey Braille for labels, or you might want to read a novel, in which case you might prefer to have an overlay that's more geared towards literary Braille.
Oh, I see. Okay, thank you.
I was wondering, originally they had talked about it being a product of science and the music department, and I can't remember what the other, engineering maybe?
That's right, yeah.
A few, but I thought, so that they're still working on possibly using it so someone could actually see the staff on
Yeah, I mean,
instead of using Braille music.
well, I'm the person in the music department. I mean, I think Braille music had been our primary target because it is a spatial code, but there's no reason why you couldn't render a staff. I just don't know, because there's a lot of information on the staff as well as the notes, whether, because it has all the slurs, and yeah, it could be very cluttered. Now, that's not to say you couldn't come up with a representation which would at least allow you to sort of feel the notes, just so you could get a sense of where they're going, because I think that might be quite a useful thing to do, even if you only had to do it part by part, just to kind of you can't do that in Braille. You can't just sort of run your hand over the Braille and say, oh, well, the melody's going to go up and then it's going to go down. So as you say, there might be some use in being able to render even that part.
Braille music is rather complicated.
It is, it's horrendously complicated.
If you're trying to do, it's okay if you're doing one line.
Yeah.
But if you're doing chords.
It's horrible.
It's a pain in the ass.
Yeah. Yep, I've been there.
I'm a Braille reader who used it all her life.
Yeah. But, so yeah, I think there could be some value. As I say, I don't know whether the staff notation lends itself very well to being explored tactilely, because it, I think, could get very crowded very quickly. But
I'm intrigued by this whole process of graphics changing as you watch them,
yeah.
as you look at them. It reminds me a little bit of a moving picture, as sighted people see on a screen what happens. Things constantly change. But this concept of a graphic changing under your fingers and becoming something different almost makes me dizzy.
Yes.
The idea is just,
It is, and
unsettling.
and if you come up and try the
When I
graffiti,
see Braille, I like to see it stay put.
stay put. Yeah. But there might be ways to do it where it's not so aggressively dynamic. But you might, for instance, say, okay, let's see what this pendulum simulation feels like, and could put your whole hand down on it and just get the general gist. Oh, right, it's kind of behaving as I expect. I don't think you'll be able to watch a movie on a tactile display. I don't think that's ever going to work. I don't think you'd want to.
Any other questions? Okay, Sheila will be up at table 20 in the lobby. If you want to stop by and give her your contact information or see the device that they've been working on.
Well, it's not ours actually. This is the AVH one. Yeah.
Sorry, the AVH one.
Yeah.
Thank you, Sheila.
Thank you. Thank you, everyone, for questions.